Morena koutou, and welcome to another Research Symposium talk, which is the third of four for Katrina. I'm going to open us up with a karakia. Whakataka te hau ki te uru, whakataka te hau ki te tonga. Kia mā kina kina ki uta, kia mā taratara ki tai. E he aki ana te atākura, he tio, he huka, he hauhu, ti hei mori ora. And I'll hand over to you, Katrina.
Okay, thanks, Stacey. Okay, so today we have a bit of a grab bag of topics. So I'll switch to my slides. We'll go share. I don't know why I say this out loud every single time. Here we go, screen 2, share. Yes, and I will put that onto that. Right, so I am sharing the right screen, aren't I, Stacey?
Yes, you are.
Okay, thank you. Right, off we go. So a different setup from the last one. So we will go to this. So today I'm going to talk about a few different things. So correlation, which is a pet subject, ratios, I mean, there's lots you can say about ratios, but more about how it's just picking up on a common way that might get misinterpreted sometimes. So just clarifying that, and also just touching on meta-analyses. Okay, so correlation. So the degree of association between two independent continuous variables, and I've underlined independent because correlations get misused a bit. And I'm not going into this in much depth, but just to say something that comes across quite a bit, particularly in our line of work, is you might be comparing two measurements of the same thing. So you've got the traditional way something's measured, and then you're trying out, or someone is trying out a new device that measures the same thing but might be cheaper or a bit more portable or a bit something like that. And so you're measuring two different techniques, measuring the same underlying signal. They aren't independent measurements, and so they should not be assessed with a correlation. And you see it happen a lot, and it's wrong. So you can look at the scatter plot between the two, but you don't actually look at the R values. So I've just talked all about correlation without talking about correlation. So we'll come back to that, but bear that in mind. And I'll come back to it at the end, hopefully. So with anything like this, so it's comparing two continuous variables. So like anything, plot the data first. Okay, we have two variables. We know from two talks ago that's a scatter plot. And we look to see, is the relationship linear or monotonic? And if it is, we can go ahead and quantify it. And if it's not, then you don't. And that may sound a bit silly, but don't just stick a line through it and quantify that relationship. It has to be linear or monotonic. And I'm going to show you what monotonic is in a minute. And so you're looking at a relationship, so you visualize it first. And then, if you can quantify it. And that quantification is with a correlation coefficient. And there are two main types of that, Pearson's or Spearman's. And you can get kind of details about how they get represented, but essentially it's a lowercase r. And what this says is the strength of the linear relationship between two numeric variables. That's the Pearson correlation coefficient. Spearman's, which I'm not going to spend too much time on, that's the strength of the monotonic relationship between two numeric variables. And this correlation coefficient can range from -1 to +1. So the closer it is to those two extremes, the greater the strength of the relationship, and the closer to 0, there's no real relationship between them. So we'll do some pictures first, because I think it's all about the visuals here, because that's what it's all about, is this picture of the relationship. So here's the Pearson correlation coefficient, and this is the one that you most often hear. I'm adding these names just because there is a difference, but when people say correlation coefficient, typically this is what they're talking about. And these are some very nice schema called off the internet. So a positive correlation, so the line goes, as one variable goes up, the other variable goes up. So it's this linear positive. As one goes up, the other goes down. Would end up with a negative linear correlation. That's the middle plot here. And you can see I very obviously put linear in on top of this, superimposed the word linear on top of the existing schema of the internet, because that's the important thing to think about here. It's got to be linear. excuse me, and then no a scattering of points everywhere. There's no linear correlation in there. So that's okay. Spearman, which we don't hear much about, but this is what it actually does. So this is all this monotonic idea. So here we've got, and monotonic means as that there's an increase in one variable while there's an increase in another variable. It doesn't have to be linear. It doesn't have to be a step-by-step kind of equal increase. So it can be as long as they're kind of increasing. And so that's what the second plot here is trying to show. This is classed as monotonic because for every one increase on one axis, the other axis is increasing as well, just not to the same degree. So you connect that with these kind of non-linear relationships, but it's still positive monotonic. But if you have a bidirectional movement, then it's not monotonic. So mono being one kind of tone, one direction. Okay. So here we go back to correlations, and these are my fabricated plots that I've probably shown many times over the years, but they work. And just think to yourself, and if not, I'm going to ask Stacey, what? Sorry, Stacey, but that's what you get for being the person in person. Is what data could a correlation coefficient be used for? And so if we think about this, and we think of our definitions, so you've got a linear increase or a monotonic increase. I shouldn't say increase, sorry. A linear or a monotonic relationship between two continuous variables. And don't worry, Stacey, I'm not actually going to ask you. So the first one, and we just think about this to yourself. Here's the answer. The lines are what the computer saw, if you like. And so the first one, top left, is a linear relationship. And we can see if the computer was going to stick, I can say the computer, the software, if you put a linear relationship through it, as you would with the Pearson's correlation, you can see that fits quite well. So that's this top left one here. So that's kind of a standard one. This next one, so top right, my cursor's not showing very well. I think we would have seen before that that goes up and then goes down. So it's not linear and it's not monotonic because it's got this two direction. So it's not going to be suitable for a correlation coefficient. And when we put through a line, which is what any computer would see, it's not showing that association between those two variables. It just cuts through the middle of that curve. So you wouldn't do a correlation for that. Bottom left, beforehand, it looked like, well, this is all quite linear. It's only one dot that's out. And so that could have been, be worth a go with a correlation. But when we see what the computer sees, if you stick a line through it, if you like, or if you're going to assess a correlation, it's not going to represent that relationship whatsoever. It's totally skewed, pulled up by the single high value there. So, in theory, you might have been able to do a correlation, but when you see the data, you can see actually, no, it's not going to work. It's not going to represent that association. And then the last one's pretty obvious at the bottom right. It's all about there is no linear relationship. There's no monotonic relationship. Okay, so you'd actually end up only putting it using a correlation for the first plot. Now, what we see often in this seems kind of obvious, I appreciate that, but I use these kind of quite screamingly obvious examples, well, with a bit of a question about this outlier, because quite often we see correlations without seeing the plots. Quite often it's just the R value, if you like, that's reported, the R statistic. And if everyone always looked at their data first and then decided if a correlation was suitable based on what we just seen here with these examples, then that would be fine to just see the R value. But as it is, many people don't look at their plots. And so we don't know what's that R actually showing. Is it a linear relationship? Because here, if we were to calculate this R, they would have exactly the same value and of 0.8, and yet only one of them is valid. 0.8 does not show those relationships for the rest of them. So seeing just an R value, or whatever you want to call it, just the numbers on their own is not helpful at all, unless you know that it's been sensibly done. So always, so I harp on about this, but I've seen it so many times. I look around posters at conferences. It's a bit like 3D plots of posters at conferences, but I see correlations done in and you just think, but I know that that variable is, some things variables that we're familiar with, measurements we're familiar with. In my case, I do a lot with NT-proBNP or creatinine. It's skewed distribution. The relationships aren't going to be linear, or they're going to be a bit weird. And yet you see this R value, magical R value stuck in. Okay. So then you see I've also added a p-value here, and for all of these, and this is genuine data, they are all, this p is less than 0.0025. And we know from my p-value talk I should have written that as p equals 0.0025 because it's not less than 0.001. So always write the exact number. And so the p-value's here. So whenever we see a p-value, we think, what's the null hypothesis? What are we actually testing here? And for a correlation, the null hypothesis is that the correlation is zero, so no difference, that there is zero. So that previously we've used language of no difference. The equivalent for a correlation is that the correlation is zero, that there is no correlation. So the alternative hypothesis is that the correlation isn't zero. So it's fine. So here, what this p-value is saying is that all that's saying is that there's insufficient evidence to suggest that the correlation is zero because we stuck the straight line through this data. Now, the straight line only fits the top left plot, so it's all meaningless for the rest of it, for the other three plots. Okay, so another thing that comes up is p-values, when it comes to correlations, they have a use, but they're of limited use. The main thing is the R value. And so the P is just kind of in the background, because if you had a large sample, you're going to get a highly significant p-value. As we see here, we get statistically significant p-values for these plots, and they're not even linear correlations. So yeah, this is a case where p-values are just of minor importance. It's all about the R value. Closer it is to +1 or -1, the stronger the relationship between those two variables. Okay. So as you can tell, I'm harping on, is this really correlation? And this is, as you can see from the axes, these are echo. These are actually from a paper about Doppler. Echo, it's an old one. Oh, it's not that old, actually. Well, actually, it is old now. And do you think that shows a low? So the R value they reported was minus, on the left graph, minus 0.39. So that's a negative relationship. That's kind of close to moderately strong negative relationship. And it's clearly not. It's a curve. Let's see if my cursor works. Yeah. Okay. The one on this side, on the right, sorry, apparently has a moderately strong linear negative relationship. Now, I'd say, and these were Pearson correlations, so it could be the second one, the plot on the right rather, could have been analysed with a Spearman correlation. They didn't, because it's monotonic decreasing. Still got a curve, but they didn't, and so they stuck a straight line through it. And they even showed the plots. This doesn't often happen. So if we just saw the results, minus 0.39 and minus 0.74, we go, oh, okay, that's quite related. But here they even showed the plots, but still stuck a straight line through it. So you can see, use always, and this was published, these things get through quite commonly, but if you're reading this kind of stuff, go, actually, that doesn't look right. And, trust yourself on this, it's not right. Another one, just because, yeah, I said that. This is another one that's a bit of a fave, because this is just bizarre. These people showed all their plots, and this is calcium scoring, coronary artery calcium. This is an old paper, but they showed them, and it's still wrong. And it's bizarre. Okay. And print all these little results at the bottom, but they are all meaningless. And apologies to these authors. I'm sorry to use their example. I don't name them. Okay. So that's correlations. So please keep an eye out for that. Ratios. So here, I was just going to talk about relative risk, or risk ratios, so the same thing, versus odds ratios. And I think we're okay with this, but I just about how to interpret them. So we know they're different calculations. They come up a lot in, well, in a lot of medical literature, and particularly epidemiology, public health, but a lot of things come up with risk ratios. So just as a reminder, a risk ratio is a ratio of two risks. Who'd have thought? So we have the risk in group 1 over the risk in group 2. And I've got here order matters off to the side. So, because I think it's, sometimes it's not so intuitive if you're creating these, from your own research or thinking about them, what order to put these in. But essentially, whatever your group of interest is, that is called group 1, if you like. So put that on top. But you can do the calculation either which way, but it's how you interpret it. When you come to interpret it, you've got to make sure it's the right interpretation for what you're doing. Okay. So anyway, risk in group 1 is greater than the risk in group 2, your relative risk will be greater than 1. So that's just fractions. All these things are just fractions. We've been doing them for decades. So if you have a higher number in the numerator, the top number, than the bottom, then you're going to have a risk ratio. The ratio between them is going to be greater than 1. Okay, so they're just ratios. Now, how we interpret this. So here's this example, which is actually a true one. So we know that women who have gestational diabetes, so diabetes only during pregnancy, that they do have an increased risk of developing CVD. And so here's a study that compared women who had GDM during pregnancy versus women who didn't have GDM, and what's their risk of developing CVD. And it should be within a certain time frame, like say within 10 years, but I didn't get into all that here. Because when you have a risk over time, it's more meaningful. So anyway, the result here in this particular study was a relative risk of 1.45, and they reported a confidence interval as you should. So the way you'd interpret this, compared to women without gestational diabetes, women who experience gestational diabetes were at 45% increased risk of developing CVD on average. Okay, so it's all about the percentage increased risk. Another way of talking about it, which is a bit clunky, but it's GDM is associated with a 1.45-fold increased risk of developing CVD. And that's clunky when we have this kind of 1.45, but you think if it was 1.98 or 2, that your relative risk was 2, then you say a 2-fold increase, things like that. And you hear that a bit more in public health and epidemiology, but that's where the folds come from. And it's all about increased in risk. It's risk ratio, it's about risk. Makes sense. So then the reason I say all this is that we compare it to the odds ratio. And yes, I have just replaced the word risk with odds in all of this. That part's exactly the same. Do the same calculation. It's, it's odds in one over the odds in other. Direction of the ratios mean the same thing, but the difference comes in how it's interpreted. So we think of what odds are, and it is an odd thing. And the way that I always kind of think of odds, because it's not intuitive, is, if I ever get lost, I always come back to a nice simple example. So one day of the week is Monday, and 6 days of the week aren't. So the odds of the day being Monday is 1 to 6. Or if you calculate that out, it's 0.17 as a percentage, or as a proportion. Okay, so that's 1 to 6. And you compare that to, if we were talking risk, the risk of the day being Monday is 1 out of 7. And so it's a different percentage. It's 0.14, 14%. And so it's, yeah. Okay, so we think of that. That's what our odds are. It's 1 to 6. So it's not out of the total, it's out of what's left over. So then if we have an odds ratio, so if we use the same example of our gestational diabetes and say what was being reported was an odds ratio of 1.45, so this is how it's interpreted. So compared to women without GDM, women who did have it were at 1.45 higher odds of developing CVD. And that, it does sound clunky, but that is how it's interpreted. It's 1.45 higher odds. And I think, have I got the next one? Yes. The only other way of saying it is you have a 45% increase in odds of developing CVD. Well, what's a 45 increase in odds? But that's what it is. And see, the reason I go on about this is because what some sometimes see come out is that people still end up calling it a 45% increase in risk, even though it's odds ratios. And they mean very different things. So, yeah, always look back and say if you're reading a paper or reading something that's been reported, always take note to say, is it an odds ratio or a risk ratio? Because quite often it's one or the other, or a hazard ratio, which I'll come to next talk. And hazard ratios are a type of relative risk. They just got time incorporated. So hazard ratio, relative risk ratio, whatever combo, that's a similar interpretation. Odds ratio is out on its own. It's a bit odd. And so you have an odd interpretation. Don't be tempted to call it risk. It's never risk. Okay. So that's that. Now, did I say anything? Oh, yes, I do have one more thing. So these are just some points about risk ratios and odds ratios. Now, we've probably heard of this as well, is that the rare, you can say odds ratios can end up calculating out to be very similar to a risk ratio when the event or the thing of interest, the numerator, is rare. So when it's here in about less than 10% of the time, roughly, you can end up with quite similar results. But that's in rare circumstances. Anything else, odds ratio is likely to overestimate the effect. So compared to a relative risk. So you still report an odds ratio if that's the outcome of the analysis that's been done. That's perfectly fine. But if someone mistakenly interprets it as a risk instead of odds, it's going to have more of an impact the more common the condition or whatever it is that's been measured. Okay, so it does become more of an issue. And you'd like to think that journals and all that all gets screened out, but it doesn't necessarily. Not all journals have statistical reviewers. More and more do, and the big journals do. But things can get through, and particularly in old literature, you might see it more often misinterpreted. Similar with the correlations. They still get through, though, bad correlations. But anyway, so just because it gets through doesn't mean what someone else has written is completely right or interpreted well. Okay, the other thing is p-values and confidence intervals. So I didn't go into it here because it all just gets a bit wordy and lots of numbers, but as with everything, you can have a risk ratio, an odds ratio if you have a null hypothesis and you can test it with a test certificate, you can get a p-value out of it in a confidence interval. And so every relative risk, if it's a result, every risk ratio or every odds ratio, if it's a result of something, should be reported with a confidence interval and or a p-value. And so previously, when we were talking about p-values and null hypotheses and all that, we talk about the difference being zero. There's no difference between them, this kind of thing, for a null hypothesis. When it comes to ratios, the no difference is when there's a one-to-one ratio. So, you think there's no difference between them. It's 1-to-1. It's not not greater than the other. So the null hypothesis when you're comparing ratios is that the ratio is 1. It's 1-to-1 is 1. So if you have a ratio of 1 within your 95% confidence interval, or your result is 1 exactly, then it's not going to be statistically significantly different from the null hypothesis. Okay, I just said that in a rather complicated way. But in essence, the point I was trying to make is it's not always 0, it's a null hypothesis. Sometimes it's 1 if it's a ratio. And it makes sense when you think about it. Okay, so that is the two main kind of ratios and just to be aware of if you're reading or talking about them. And so next thing I was going to go into meta-analysis. That's what I'm up to. Okay, so these get reported quite a lot. There's a lot of different types. As there's more and more research done in the past, as there is, people are more likely to want to aggregate and pool those results of individual studies as if they were one much larger study. And so it's a way of increasing your statistical power. So if you have a number of smallish studies, and you often, it's unavoidable if you have kind of a rare condition or things like that, no one study is going to give the definitive answer. So because there's just not enough of those people with that condition or circumstance, or it might be new, and a lot of smaller studies being done really in a hurry. You saw these a lot in COVID times. A lot of things were getting done in a hurry when COVID first hit. And so there were a lot of publications very quickly. Reviewing was overtime, good grief. We did very quick turnaround reviewing, but also a lot of meta-analyses were done quickly too, because to try and pull these results into something more meaningful. It increases the precision of a result. More studies equals equivalent to more patients, more participants, and so the bigger the sample size, the greater the precision of a result. And it can sometimes settle controversies or conflicting findings. That's the theory. It doesn't always work, but that's what it's for. Meta-analyses are quite common, and a well-done meta-analysis is really useful. So this is what a meta-analysis result might look like. This particular study is about asthma, and they were looking at some kind of digital intervention, and I can't remember the specifics of that. That was the intervention, was a digital thing. It might have been an e-tool to help people. I can't remember actually, I shouldn't guess. But it's to do with exacerbations so an event is an exacerbation of asthma. And so the intervention is this digital intervention versus a control, which was usual care. Okay, so what we see is this table and a figure. So on the left is called a forest plot, and on the right is a table. And so what we have, we've got to try and look into what's all this. It looks like massive numbers and studies. So here we have our intervention. Columns next to it is the control results, and they get summarized for each study, which is each row. They get summarized into this case, it's a risk ratio, and we know all about risk ratios now. So risk ratio or relative risk. So that's nice. So it's not an odds ratio, because you can do whatever you like here, but these authors sensibly chose a risk ratio. Okay, so if we delve into one study, and I actually do this, if it's something I'm particularly interested in, I do actually read the table properly, which may sound a bit facetious, but I do actually, sometimes you skim through and go, oh, yeah, they've got a result, that's nice, we'll just look at the result. But I do always like to get my head into what's actually happening here. So this study, I've just paid a pink highlight, Vandermeer, we'll just pick one of them. And we can see the first results are that this study had 91 people in the intervention group, of whom 11 had an event, in this case, exacerbation of asthma. And so I just like to kind of do a quick check of a risk ratio myself. And we end up with a 0.12 probability, or 12% percentage, 12% risk of having exacerbation of asthma in the intervention group in this study. The next two columns are the control group. So there were 92 people in the control group, and 10 of them had an event. And so we check that out, and that is 11%. So that's nice. And then we look at the results, so we can create our own risk ratio. We've just done them. It's just the risk in one group over the risk in the other group, and it ends up being a risk ratio of 1.11. And we can see that that's exactly what they reported, which is quite nice. So 1.11, and they have a confidence interval of, so I have to look to my biggest screen here, 0.5 to 2.5. So it's quite a wide confidence interval around that. And so we get what these statistics are that are being reported in this table. Okay. We have 6 studies, and they should always be reported with something identifying. It's usually the first author's name and the year in which they happened. Sometimes it's quite nice to have them sorted by the oldest study at the top and the newest at the bottom, or vice versa, but just so we see any shift over time and the kind of results that were coming out about this, because the time shift is useful. And then the other piece of information on the table to start with are their weights. And so a meta-analysis, we say it's combining results of lots of studies. You can't just bung them all together. It's a weighted average of all those studies. And how do you weight them? You tend to weight them, the default way is by study size. And so we can see here in that column, the top one, Chan 2015 is given the greatest weight of almost 40% in the final result. And that's because that's actually the biggest study as well. So it's based on study size. It's all got a few other details in there as well for the weighting, but mostly it's about study size that gives that weight. So bigger studies are going to have the greatest influence, which is kind of good, but also you wonder sometimes, you know. Anyway, so that is the layout of the table. Now, one thing I didn't actually circle, I've just realized, what we see down here is heterogeneity. See this? It's always in the output, heterogeneity. They've got a chi-squared of something or other, degrees of freedom of something or other, and an I-squared value here. And the I-squared is the main go-to about heterogeneity. So heterogeneity is how much variation is there between studies. And it's a percentage from 0 to 100. 37% is not too high. You can see some that are closer to 100%. And so you kind of high heterogeneity, you wonder if those studies should be combined, you know, because there's something quite different about them. And so a good meta-analysis would go off and say, oh, this heterogeneity is kind of high. They'll go off to analyze where it comes from. Is it different eras of time? Did they have, you know, and there was a change in treatment perhaps along the way? Were they, you particularly see it in time to follow-up studies, they have a different duration of follow-up. That's quite common, and that can cause that heterogeneity. Or different countries, or some are only men, and studies have only men in them, or things like this. So you look into those sources of big differences. In this case, this heterogeneity, 37%, I wouldn't worry about it too much, even though it seems like a decent amount, but it's not too bad. Okay, what else do I go to? Oh, and the final result, that's what we're getting to as well. That's over here on the bottom of the table of 0.51 with a confidence interval. So 0.51, and it's a risk ratio. So the intervention is what we're interested in. So you can imagine that's on the numerator of the risk ratio. So you half, people who have this intervention are, on average, are half as likely to have an exacerbation of asthma than people who aren't, in round terms. And you see the confidence interval, it's a 95% confidence interval, and we can see that goes from 0.3 to 0.4 to 0.8 with rounding. And so 1, the null value, is not in that confidence interval. And so this is a statistically significantly different result from the null hypothesis. Okay, so the evidence, combined evidence, is that there is definitely a reduction in exacerbations with the intervention. Okay, that's the table. Now we look at the figure, and sometimes it's quite nice to just look at the figure first, which you do if you're just reading through something. So here, the size of the box is related to the study size, and we can see Chan at the top is the biggest box, and they have the highest weight, as we've said. So that matches. Here, we've talked about our null value as 1, because it's a ratio. So the and 4 of these 6 studies cross that null value. So their confidence interval, which is shown by the thin line, crosses the null. And so those 4 studies have non-statistically significant results. But this study just does, and that big study does, have a statistically significant result because their confidence interval doesn't include 1 for a ratio. And there's our study we've just been looking at, Vandermeer. I've drawn all over it, unfortunately, sorry, but we know from our calculation, so that had a risk ratio of 1.11. And if we just looked at the plot, we'd see, oh, the confidence interval is crossing the null, so that's got to be a non-significant result. And we know back from when we calculated it, we had 1.11 with this wide confidence interval, so it clearly was not statistically significant as well. So, you know, we're seeing the right data, is what I'm saying there. What do I have next on this slide? Oh, yeah, that's it. So we know the figure should represent the numbers. The figure is a nice, or the forest plot is a nice kind of summary straight off. But we can always look into more meaning from the table. So here, the final result, which we talked about already in the table, is where this is. And so overall, it's a statistically significantly different from one. And this is the joy, if you like, of a meta-analysis that is dominated by this big result from Chan and then supported by this one result from Zhu. So these 4 studies, 2 of them were kind of, I don't want to say trending down, but they suggested a similar direction of result. These 2 smaller studies had no, could have gone either way kind of result. So it's interesting here that this is, you go, okay, well, a meta-analysis result is what it is. This is fine. That's what the analysis showed. But bear in mind, it is influenced by one study. So personally, I would say I'd like to see a few more studies done on this, because I'm still not convinced about that. Because what is it that's unique about this study here that what could be unique about that study that might be influencing this result a lot? Okay, and that is meta-analyses. That's right. I mean, there is a lot more to it, and there's lots of other plots that can be done. But that is, if you're reading one, how to get the guts out of it and how to kind of critically think about what the numbers are. And that's where I thought I'd stop on that one. That's part 3 done. Okay.
Beautiful. Thank you so much.
All good. All
I
good.
really appreciated the meta-analysis one. That was great.
Oh, good.
Yeah.
Excellent. Excellent. I'll better stop sharing. Good.
Right. Well, I will close us off with a karakia. So your next talk, Katrina, is regression and survival analysis. So sounds like a goodie. And we look forward to it.
Oh, thank you. And that's next Wednesday, isn't it?
Yes.
Yeah.
And then the symposium's rounding off with Rob the next day.
Right. You can do the grand finale. Excellent.
Yeah. All right. Kia whakaaria te tapu, kia wātia ai te ara, kia turiki whakataka ai, kia turiki whakataha ai, haumie, uie, taikie.
Thank you. Thank you.
I'm just